So, today we're going to learn how to do a coordinate proof. And there are three things you need to do for a coordinate proof. The first thing you need to do is locate the proof. Then you need to have the steps for the proof. And then we're going to do a practice proof. So the first thing you do when you locate a figure is you should use the origin as a vertex, because that way you have 0, 0, and they're easy numbers to work with. The second thing you should do is place at least one of the sides on an axis. So the points would be 0, 0, and A 0, 0, 0, and 0A. Again, you have zeros and they're easy numbers to work with. The third thing you should do is keep the figure in the first quadrant so all the numbers are positive and you have no negative numbers, because why make your life harder? Then, you should use whole numbers because, again, why would you make your life harder? Now the fifth thing you should do, this is required. You have to do this. You have to use letters instead of numbers when you're writing the coordinates. And that way, you're proving that the figure in that category, the statement is true for any figure in that category and not just the figure with those particular numbers. The sixth is also required because you need to make sure your figure doesn't assume too much. So if you're proving something about an isosceles triangle, don't make it an isosceles right triangle by doing this and putting two sides on an axis rather than just one. Okay, so in order to help you understand how to do a coordinate proof, we're going to do a practice proof. So we're going to practice number 21 in the textbook. So the measure of the segment, we're going to prove that the measure of the segment that joins the vertex of the right angle in a right triangle to the midpoint of the hypotenuse is half the measure of the hypotenuse. First thing we do for a proof is step 1, which is to write the given and the proof. And for this problem, we're given right triangle ABC with right angle BAC, and we know that P is the midpoint of BC. We're trying to prove that AP equals 1/2 of BC, or the hypotenuse. Now we've written the given and the proof, we proceed to step 2, which means locating the figure. So, notice how I kept the vertex at the origin, and I kept the figure within the first quadrant, so all the numbers are positive. I made sure that I wrote letters instead of numbers with the exception of 0, so that this statement is true for any figure in this category and not just a figure with particular numbers. I also made sure that the figure didn't assume too much because this is not an isosceles right triangle, but just a right triangle. So when deciding how to prove your proof, you can either use the slope formula or the distance formula. In this case, it would be very helpful to use the distance formula because we're trying to prove that AP is 1/2 the measure of BC. We would use the slope formula if we were going to prove that something was parallel to something else or perpendicular to something else, but since we're not, it's not going to be of any use to us. Okay, so now we're at step 4, where we're going to use algebra to prove our statement and show all our work. So we know that B is 0, 2B, and C is 2C, 0. We need to solve for P, so we can find the coordinates of P. So using the midpoint formula, which is x1 plus x2 over 2 and y1 plus y2 over 2, we're going to plug these points in where we solve, so 0 plus 2c over 2 and 2b plus 0 over 2, which simplifies to cb. So now we know that P is cb. What we're going to do now is we're going to find the distance between A and P to prove that it's half of BC, and we're also going to find the distance of BC. So we're going to use the distance formula, which is the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared, which is, so we're plugging in the points. We get the square root of 0 minus c whole squared plus 0 minus b whole squared, and that simplifies down to AP equals the square root of c squared plus b squared. Now we know that the distance between AP is the square root of c squared plus b squared. So what we're going to do now is we're going to find the distance of BC, which, again, we're going to use the distance formula and plug in the points. You'd get the square root of 2c minus 0 whole squared plus 0 minus 2b whole squared, which simplifies down to 2 times c squared plus the square root of c squared plus b squared. So we know that bc is the square root of c squared plus b squared. Now we know that we've proven the distances, that AP equals 1/2 of BC, or the square root of c squared plus b squared equals half times 2 times the square root of c squared plus b squared. Okay, so now we've reached the end of our proof, which is step 5, to write the concluding statement that summarizes what we did. So, using the midpoint formula, we found the coordinates of P, which were C and B. Then, we found the distances of AP and BC to prove that AP is 1/2 BC.
So today I'm going to teach you how to prove that two triangles are congruent. There are 5 different ways. There's CPCTC, SSS, SAS, AAS, and ASA. So CPCTC is pretty simple. It stands for corresponding parts of congruent triangles are congruent. You can state CPCTC in a proof, and it proves that two triangles are congruent. So SSS stands for side, 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 and it's when 3 sides of a triangle are congruent. You can prove that two triangles are congruent if their sides are all congruent. Okay, so SAS is side, angle, side, and if 2 sides and an included angle are congruent in 2 separate triangles, then the triangles are congruent. So AAS is angle, angle, side. If 2 pairs of corresponding non-included sides are congruent, then the 2 triangles are congruent. So these are the non-included sides, and if those are congruent, then both triangles are congruent. So ASA is angle, side, angle, and it's pretty simple because it's the 2 pairs of corresponding angles and their included side are congruent, then both triangles are congruent. I'm going to do a practice proof to just show you in what context we use the different ways of proving that two triangles are congruent. So we're using AAS in this proof, and so let's start. So the given is B is the midpoint of YW, and we know that these two are parallel, so UY is parallel to XW, and what we have to prove is that the two triangles are congruent. So in step 1, we state the given, and we write whatever the given was in the first step. Step 2 is we're going to use the midpoint theorem and say that YV is congruent to VW. So we use the midpoint theorem for that. And in step 3, we use the alternate interior angles theorem to prove that VWX, this angle, is congruent to VYU. So these two angles are congruent with the alternate interior angles theorem. And in the 4th step, we use the same theorem to prove that angle VUY is congruent to VXW. So these two are congruent. So now that we know that we have AAS, we can state that in our final step and prove that these two triangles are congruent.
Okay, so now we've reached the end of our chapter 4, and I'm going to teach you about transformations. So a transformation is an operation that maps an original geometric figure onto a new figure, and this could change the position, the shape, or the size of the figure. Now the pre-image is the original figure, and the image is the new figure. So there are 3 types of transformations. There's a reflection, which is a transformation over a line of reflection. There's a translation, which is like sliding, so a translation that moves all of the points of the same figure in the same direction, the same amount of distance. The final transformation is a rotation, which is a turn around a fixed point, which is the center of rotation, through a specific angle and in a specific direction. Okay, so there are 3 types of transformations, as I just said. These are examples. So these are the reflection, where it reflects across the line of reflection. Translation, which is just like slide, and slide to the rotation, which turns around a fixed point through a specific angle in the specific direction. So, this direction. So now, I'm sure this is all pretty clear, but just to make sure, we're going to do a couple practice problems. So, we're going to name the transformation. This is a reflection, and that's because it transforms over a line of reflection, and each point of the pre-image and the image are the same distance away from the reflection. So this is the same distance away from the line of reflection as is this. Now the second problem is a bit harder because it could be one of two things. It could be a translation because it moves all the points of the original figure in the same distance in the same direction. But it could also potentially be a reflection because each point of the pre-image and the image are the same distance from this